Hi students, a very warm welcome to you all to the chemistry sessions, and this time we are going to have a questionnaire round. So I need to test your knowledge whether you have listened and followed up all the sessions or not. So basically what we are going to discuss is about the NEET pattern exercise for isomerism. Those who are not giving up NEET, that means those students which are not the bio ones, right? This particular exercise is yet very important for you as well, because the level of NEET is, you can say, a slightly higher than what we have in CBSE. So it will be a very good practice for you as well. So let us just move on to the question number 1. Which of the following biphenyls is optically active? Right. So here we are talking about the biphenyls. As I told you in the session, whenever there is the existence of a biphenyl, what is biphenyl? Phenyls, right? Joined together like this. And these two biphenyls will always be optically active whenever. What is the condition for a biphenyl to be optically active? The condition is the ortho substitution, right? So that is what we have discussed. So basically I need to find out which is optically active, having a proper ortho substitution. So over here, if I start by option number D, right? You can very well see over here what are the ortho substitutions with respect to a particular group. That means if I consider this benzene and a substitution here onto the benzene, that means for another phenyl group is substituted, then with respect to this phenyl, this will be ortho and this will be ortho, right? And similar will be, these are two ortho positions, clear? So first and foremost we need to find out what ortho position is. I have found out, I cannot see any substitution over here but simply the hydrogens. That means this particular compound will not be giving any optical activity, because why ortho substituted will be giving the optical activity? Due to the steric hindrances, the two ring go out of the plane. That means if one ring is like this, the other is perpendicular to the previous one, right? So that is how the rings have been arranged and that is how they show the optical activity, clear? Now let's move on to option number C. In one of the phenyls there is ortho substitution, but in the other one, again there is only the hydrogens, no such bulkiness present. So it's improper, we can say, improper substitution, right? So this is also not giving up the optical activity. What else? I've got number B. Again here you can see these places are still unoccupied, still don't have a bulky group present, right? That means this will also not give. What about the option number A? It's very well visible. Merely by looking onto the options, I can get the idea whether which compound will be optically active or not. Just you need to look at the ortho substitutions. I can very well see the ortho substitutions, and that too by very bulky groups, right? Iodine is bigger in size, bromine is bigger in size. So it will definitely be giving optical activity, clear? So the option is, the right option is A, clear? Now let us just move on to the question number 2. Yes. Now it's a very interesting question right here and is related to nothing but tautomerism, right? Which among the given molecules can exhibit the tautomerism? I need to find out of the 3 which will be giving the tautomerism, or it may be more than one as well, right? So as I look for tautomerism, what do we observe first thing? For a tautomerism, for an compound to exhibit tautomerism, I need to look for the alpha hydrogens, that is the acidic hydrogens, right? That is the main key point over here. And how do we actually show a tautomerism happening in a molecule? Whenever we have got such kind of a compound. It's just an example that I am giving. So this particular alpha hydrogen, right, this is also alpha. This alpha hydrogen is attracted by the oxygen, and that is how this hydrogen is transferred momentarily and will be giving the enol form, right? Everybody remembers that? Now, I need to check the options one by one. I am concerned first of all with this keto group, right? That is how we will be having a tautomer, right? So first is the keto group. I need to look the hydrogens present on either sides of it. Those are only the alpha hydrogens. So if I observe over here, I have got one hydrogen, I have got another over here, right? Now it has got the alpha hydrogens, it will definitely be giving the tautomerism. But here you need to be very careful. I am going to introduce another topic to you, that is, here the hydrogens which are present are on the bridge. So over here these hydrogens are bridge hydrogens, that means present on the bridge. I cannot remove this hydrogen and make an enol form. Why is this so? Because whenever there is some kind of group present on the bridge, if I remove it, the bridge will break, right? So this bridge over here is quite sensitive. I cannot shift this hydrogen just like that to make an enol form. So the bridge will tend to break. The molecule will become unstable. That is why this will prefer not to show tautomerism. Clear? So this particular compound will not show tautomerism. One is not showing. Let's move on to the second one. In the second one, where do I have the hydrogens? I need to locate the alpha hydrogens again. This is the keto group. Here is the alpha hydrogen. And what else? Do we have any hydrogen over here? No, I don't have any hydrogen. All the places, all the valencies of the carbon are occupied already, right? So I am left with only one hydrogen, and that too on the bridge. Again the bridge will tend to break. Thereby this molecule will also not prefer to show tautomerism. Okay, now let's move on to the very last option. Where are the alpha hydrogens? Alpha hydrogen over here, and I have got two more over here. So if you see, this particular hydrogen is definitely not giving because it is again on the bridge. But these two hydrogens are very much willing to participate in the tautomerism because these are neither present on the bridge and nor I have got any other groups present other than hydrogen. What I need is the hydrogen which is available to me, right? So this particular molecule number 3 will definitely be giving the tautomerism. Clear? So I need to check for option number 3, that means the third molecule. I have got only one option, that is A. Clear? So that is how you need to approach, and especially in tautomerism questions, because tautomerism is such a topic, it's very much frequently repeated. So you need to be very careful while observing the molecules which are given. There will not be any simpler questions related to it, but slightly having a different logical approach. Clear? So here the logical approach was, I need to see whether the bridge is getting broken or not. Clear? Now, the next one. Right. Again the question pops up for the tautomerism. The enolic form, now they are asking about the enolic form. The enolic form of the ethyl acetoacetate, right? As below has. So they are asking about the number of sigma and the pi bonds. Don't just straight away jump onto the question, but first of all observe what all options are given. Maybe just by looking onto the options you can get the answer. So that is what, first is the observation and then you need to move on to some kind of a conclusion. Clear? So here the compound which is given is ethyl acetoacetate, and its enolic form has how many sigma bonds and how many pi bonds. First of all, I need to figure it out which is the enolic form, right? So over here in the two options, if you consider, there are 2 keto groups present right here, right? And what is the alpha hydrogen, what is the acidic hydrogen which needs to jump towards the oxygen is this particular. So this must be the keto form, and after jumping of these hydrogens, the hydrogen, one of the hydrogens has jumped and bonded with this O, and what we have got is the enol form. I hope everybody remembers what enol form is. It's ene plus ol. Why ene? A double bond is generated and ol means alcohol. So that is nothing but the enol form, right? So I need to again figure it out. What? A very simple thing. I need to just count the number of sigma and the pi bonds. Clear? So just by looking onto the pi bonds, I can strike out 2 options. Clear? So how many pi bonds do I have in this enolic form? 1 and 2, clearly visible. So that means these 2 options will be incorrect. Now I need to choose one. How many sigma bonds? Let us just count. 3 for these hydrogens, 1, 4, 5, 6, 7, right? 8, 9, 10, more than 10. It could be more than 10. I need not go further, but I can strike out this option as well, because the sigma bonds are more than 10. That means there is only one option left, is A, right? If you have got some more time, you can completely recheck the answer by just counting all of the sigma bonds. Clear? Otherwise, you can just move on to the option number A, that would be correct. Clear? So that was quite an easy one. Now the next question, which of the following acid does not exhibit optical isomerism? Now you must be observing over here that more of the questions are coming from tautomerism as well as the optical isomerism. So you must be now sure that these 2 topics must be very well understood by you, because mostly the questions arise from this topic, right? Optical as well as the tautomerism. That is the important thing over here which need to be focused. Now, which of the following acid does not exhibit, right? Exhibit optical isomerism. I need to check which of the molecule is not showing the optical isomerism, optical activity. I need to go on to the structures for each one of them. So first is the malic acid. So what is malic acid? It's something like this. That is completely a theoretical question. Why? Because you need to have a proper knowledge of each and every structure, right? Alpha amino acid. What is alpha amino acid? Any alpha amino acid they are talking about. So here I have got is amino acid. If you do not have any idea what amino acid is, amine, the name contains amine, the name contains acid, right? Clear? And what do I need to do? I need to attach some group. This is nothing but the alpha amino acid, and the name, for your information I am telling you, that is alanine, right? Next compound is lactic acid. So lactic acid is this. Tartaric acid. So we all have read these compounds earlier as well. So what is tartaric? Right? Now what do I need to do is, I need to figure it out which one will be showing optical activity. The very basic thing, the very basic approach is we need to find out the chiral centers, right? So here in the lactic acid I have got a chiral center, all the 4 groups are different. In alanine again all the 4 groups are different. In tartaric acid I have got 2 chiral centers, right? And you must be thinking that this is a meso compound and it will actually lead to optical inactivity. But I would like to tell you over here is, if this OH is shifted to the other way round like that, then this compound becomes optically active as well. So it has got 2 chiral carbons, optically active. What I am left with is malate. Why malate is not showing any optical activity? First and foremost thing, what you see over here is a double bond. I cannot decide the chirality of this compound due to this, right? So there is no chiral center present over here, thereby making malic acid not showing optical activity and the correct answer. Clear? Let us just now take up the question number 5. We have reached halfway now. Okay, seems to be a very big question, but yet it is very simple. I've got a compound over here which they have been given, has a chiral center. This compound has a chiral center. They are telling us which chiral center is there. If you figure it out, the second carbon, right? Which one of the following represents its R configuration? I just need to see which one is showing the R configuration. I need to assign the priorities and then find out the configuration of each one of them. That is what I need to do. And over here, if I start with option number D. So, out of the 3, first of all, I need to prioritize chlorine. Out of ethyl and methyl, eth, 2 carbon atoms will be given priority 2, 3, right? 1, 2, 3. The configuration is coming out to be R, but if you see, the hydrogen is on the horizontal position, and as I told you in the sessions that whenever the hydrogen is on the horizontal, I need to invert the configuration. That is my answer. So here the answer would be S, right? So this particular compound will be showing S configuration. Clear? Let's move on to the C. So here again I need to prioritize chlorine. Once I get the priority, I can assign it quickly to each one of them, right? 1, 2, 3, R configuration. H is on the vertical, it will remain the same. We get our answer. But before moving on to the next question, I will be discussing the remaining 2 options as well. So here again, chlorine 1, 2, 3. What is this? S configuration. Right or not? Now, here 1, 2, 3. 1, 2, 3. Again it is coming out to be R, but since the H is on the horizontal, I will be inverting it as S. That means out of 4, this particular is the answer, that is C. So that was quite easy. I hope everybody has got the answer right. Moving on to the 6th question. Now it's a theoretical question. You need to have a factual knowledge about it. If there is no rotation of plane polarized light by a compound in a specific solvent, though to be a chiral, it may mean that, right? So what they are saying is, there is no optical rotation by that compound, but still it is chiral. How is that possible? So let us just read the options one by one. The compound is certainly a chiral. It may or may not be chiral, but here they have already mentioned it to be chiral, right? So I don't think that this is a correct explanation because it's already mentioned in the question. The compound is certainly meso. Yes, it could be meso, because what are the meso compounds? Although they are having the chiral centers, just like what we have discussed earlier about the tartaric acid, although being chiral, having 2 chiral centers, right? Still it is optically inactive due to the presence of plane of symmetry, right? I can cut it into 2 halves, and due to the internal compensation, the optical activity will be there in this compound, So this option can be correct. There is no compound in the solvent. How is that possible? They have already mentioned that there is a compound. You need to read out the question very carefully. The compound may be a racemic mixture. So in this particular case, due to the racemic mixture, it may or may not show the optical activity. The racemic mixture may or may not be showing the optical activity. But here what they are asking is if there is no rotation of the plane polarized light by that compound. What they have said is that there is no rotation by that compound itself. So how can I talk about the racemic mixture over here? That means what will be the correct answer, what will be the correct explanation for this particular question will be B. That is, the compound would be meso, right? I hope everybody has got it, and you need to know how to analyze each and every option as per the requirement. Question number 7. The molecular formula of the diphenyl methane is given is C13H12. I do not need that. How many structural isomers are possible when one of the hydrogen is replaced by chlorine atom? I need to find out structural isomers. I am not concerned about the optical activity. Here I do not need to find out any chiral center. Simply the structures, different kind of structures, what can I obtain? I need to play with this compound. So what do I need to do? I need to replace one of the hydrogens with chlorine. So first and foremost is the thing that this particular compound is symmetrical, as you can see. For this molecule to show different structural isomers, I need to find out what all type of hydrogens are present, right? Similar kind of hydrogens. Let's just say here there are 2 hydrogens and each one of the hydrogen is same. The environment is same, right? If I replace one hydrogen with chlorine, I'll be getting the same structural isomer. If I replace this particular hydrogen with chlorine, I'll be again getting the same isomer, right? So I need to first figure it out. First is the thing that what are the type of hydrogens present, right? That will give us the complete answer, that how many structural isomers, unique structural isomers are possible, right? So if I say here these are one type of hydrogens which are present. Next is these are same, present on the ortho positions. Also these are also same, right? What else I have got is, okay, hydrogens present on the meta, these are also same, right? And finally what do I get is, yes, these are also same, right or not? So what all, how many type of hydrogens do I have here? How many type of hydrogens are there? One type, type 2, right, type 3 and type 4. That means all in all I can have how many unique structural isomers? 4. I need to replace each one of the hydrogen with chlorine atom and I'll be getting a different and a unique structural isomer. Whether I replace this or this particular hydrogen, I'll be getting same. So that will be counted as 1. Similar will be the case in these red ones and the blue ones. Clear? So number of hydrogens, unique hydrogens are 4. Thereby I get the answer as B. Clear? So that is how you need to approach in this particular question. Now let's take up the question number 8. What do I have? Yes, this particular question, okay, the compound obtained by chlorination of N-butane will be. So they have given the compound which is obtained when we chlorinate the butane. Which butane? N-butane, right? So there is no need to go into the reaction because they have already given the product. What they are asking is this product is what? What kind of a thing, right? So here, if you see, can you mark it out? Any chiral center? Can you see it? Yes, there is a chiral center over here. So this product is what? Mesoform? Is it? Is there a plane of symmetry? No. Is there a center of symmetry? Not at all. So that means this option is incorrect. Racemic mixture. Since this is chiral, it could have enantiomers, it could have D as well as L form, right? So there are two possibilities given over here as well, but I am not specific that I will be getting D form or L form, but I am specific is of option number B. That means there must be a racemic mixture formed, because I can have a D and an L form. So a mixture of enantiomers could be obtained here. That means option number B is very correct. I hope everybody has got it. It was just a very easy and a factual question. Clear? Now, next, butene exhibits cis-trans isomerism. Yes, we do know that. Due to, now they have asked the reason for that, why it is showing this cis-trans isomerism. First option. So first of all, let us just draw the structures, because here they have mentioned carbon number 2, 3, 3, 4 and whatnot, right? So what is butene? Right? I hope everybody knows the structure of it. If not, you can very well deduce it from the formula itself, from the name itself. So that is butene. I can number the carbons from either of the sides. That would be the word root, na? 1, 2, 3, 4. Right? So here, carbon number 2 and carbon number 3, they are asking. Rotation around C2, C3 double bond. So here, there is the double bond present. Can I rotate this double bond? Not at all. If I rotate it, it will break. Clear? So this option is incorrect. Rotation around C3, C4 sigma bond. C3, C4 sigma bond. This particular. By rotating such, I will be getting conformations, not cis-trans isomers. Right? Again, this is incorrect. Rotation around C1, C2 bond. Again, it will be a sigma bond rotation. Again, I will be getting the conformations, right? Not configurations. I hope everybody is clear with what conformation is and what configuration is. Clear? What I am left with is option number D. Let us just check whether it is a correct one or not. Restricted rotation around CC bond, C double bond C. So, indeed, it is very correct. That is the only condition for a molecule to exhibit cis-trans isomerism, that is, there should be restricted rotation. That is why we are getting two isomers here in this case. One is the cis, in which the bulkier groups are on the same side, and one is the trans, in which the bulkier groups are on the opposite sides, right? So that is cis and that is trans. Clear? The molecule is not able to rotate via this, about this double bond. That is why there is only the rearrangement of these groups or the substitutions. Clear? So that is what the criteria for a molecule to exhibit geometrical isomerism is. I hope that is clear to you. So let us just move on to the very last question of this questionnaire round. Okay, again related to cis-trans isomerism. So basically, which of the following will not show cis-trans? I need to analyze each and every option. I need to figure it out which of the molecules will show and which will not, right? So the very first, what are the conditions for a molecule to show cis-trans? First is presence of a double bond. Second, different groups on either side of double bond. Right? That is what we need to check mainly. Clear? So the number one option, there is a double bond, right? But if you see over here, what do I have? Okay, the question is which will not show the cis trans. That means out of the 4, 3 will show and 1 will not. So in the first option, I have got the first statement very correct, that is the double bond is there and the different groups on either side of the double bond. If I look on either sides, here I have got what? So, okay, over here, if I look by this side, I have got a hydrogen, I have got a methyl. Again over here, hydrogen, methyl. That means different groups on either side of the double bond. Clear? So, this will definitely be giving the geometrical isomerism, the cis trans isomerism. Now, if I move on to the next option, a double bond is there, right? I need to check the groups now. Here I have got H first, which is attached with carbon, and the ethyl which is attached. Here H and the ethyl. This will also give. If I move on to the option number C, a double bond, right? I need to check for the groups now. Here carbon attached with hydrogen and an ethyl, different groups. But over here if you look, the carbon is attached with 2 similar groups, violating the rule number 2, right? So this rule has been violated over here. This molecule cannot show cis trans, right? So this is the option number C, which is correct, right? But let us just check the last option as well. Double bond is there, right? Okay. What? Now here is H and here is ethyl present on one side. Here is H and here is isopropyl present on one side. That means definitely this will be also showing the cis trans isomerism. I am not going into the detail of what all the representations of cis and trans isomers will be. That you have to do it on your own because we have done it in the sessions as well. Clear? So I hope everybody has got it, how we are striking out the wrong answers and how we are finding out the correct ones based on a proper logical approach. Clear? So I hope everybody has tested their knowledge regarding what all we have done in the isomerism so far. I hope it was a very good session for you, and you need to revise it once again just in order to have a better practice of all the types of questions that we have discussed. Clear? Have a very good day.